You are live.
Welcome, Mike.
You can, whatever you want to do. All right. I think I know everybody here, but if I don't, Jim Bergmann. I'm actually the designer of the software program Measurequick. Some of you guys have used, some of you guys haven't, but it's been a long passion of mine. I was at Structured County Valley Career Center back when the very first, in fact, 20 years ago, you guys just think about, we just had the anniversary of 9/11, and 20 years ago there was no iPhones. Think about that for just a second. There wasn't a single smartphone in existence, right? That wasn't until a couple of years later that we had the smartphone. I think 2003, the first smartphone came out. First smartphone came out, I thought about this idea, but Apple didn't allow anybody to program for themselves at that point, so they had it all locked down for another couple of years. And I designed the first product I designed that was along these lines was the iManifold, and then eventually Measurequick was out for the universal platform. So I've been working on this for a couple of years. And the idea back then was to, when I was a gardener trained, I was a gardener trained for 15 years. I realized my entire career I'd been making measurements, but most of the time I didn't know why, right? Now, just to put this in perspective, right? If most of you guys in this room, if I asked you, hey, I told you it's it's 81 degrees in the house, or 81 degrees in your space, and it's got a 67 degree wet bulb, you know, and you've got a 92 degree outdoor air temperature, and I'll just tell you, you got 400 CFM per ton of airflow. Before you hook up your gauges, what should the pressures be, right? What should the suction line temperature be? What should the liquid line temperature be? And if you don't know, nobody ever showed you how to do your job for a living. And I found out 15, 16, 20 years in that I had no idea what I did for a living, because I had no idea how that equipment should run. And it really came back to where the whole epiphany of this came back from was this Portland temperature pressure chart. You guys ever seen on the back of that, it had TD temperature difference from like different refrigeration applications. So once I saw TD, and I was thinking, oh, temperature difference, and I noticed it was always the same. And I thought, well, why isn't it the same for air conditioning? And I found out, well, it sort of is, except it's a little bit variable because we can have like 350 CFM a ton, or 400, or 450. But it's always a function of the duct design. So you have to actually, the only way you find out the true TD is you measure it, but it does fall in a certain range. So like if you're looking at a system and it's 75 degree return air, and we know that typically the evaporator coil is 35 degrees colder. 75 minus 35 is a 40 degree evaporator. 40 degree evaporator would be about 118 pounds of pressure, right? If you have a 40 degree evaporator and you have 10 degrees required superheat, well, 40 plus 10 is a 50 degree suction line temp, right? Same thing if we had a 100 degrees condensing temp, and we were supposed to be 10 degrees of subcooling. Well, 100 minus 10 is 90 degrees, and we'd have a 90 degree liquid line temp, right? So before you hook up your gauges, you really should understand what stuff was, and that was like the first piece of understanding Measurequick. So back when I started teaching school, I started teaching the kids design temperature differences, and then, you know, I realized that every single measurement we take, every single one can be back calculated what it should be based off the load conditions.
Now, do you have a humidity sensor? Because if you have a very high humidity, your TD on your supply return will be lower because of the load.
The TD will yeah, and we recalculate that continuously. But here's another thing that the guys don't realize with a evaporator coil, just to digress for just a second. So, let me ask you guys a question. If I have a tank of refrigerant, it's, let's say in this room, and it's 70 degrees, and it's, let's just say 50% relative humidity, right? 70 degree tank, and we can measure the pressure of that tank, and it'd be, you know, whatever it is, I don't know off the top of my head what it would be. Let's say it's R12, it's 70 degrees, it's 70 pounds, it'd be 70 degrees roughly, right? Or for R12 refrigerant, since everybody in here looks R12 age, Myron. So, what are you gonna say? So, if we took that tank at 50% relative humidity, and I took it outside, and it was 70 degrees outside and 100% relative humidity, would the pressure in the tank change?
No.
Shouldn't.
It shouldn't.
No.
Are you sure?
It's going by temperature.
Well, temperature, so when we're talking about what drives what drives heat? What drives, the pressure in a tank? It's temperature difference, right?
Right.
Now, let me ask you a question. How does energy get through that tank?
Temperature difference.
Through the wall of the tank, right? So what would happen if that tank fell below the dew point temperature? What if that tank is 70 degrees, the dew point temperature, what would that tank start to do on the outside?
Oh, it's sweat.
It would
Then
sweat.
you would be adding heat to
And
it.
then we're adding heat. What kind of heat?
Latent heat.
Latent heat.
Latent heat on the outside, but it's gonna turn into sensible on the
It turns
inside.
on a sensible, it's gonna raise the pressure. It's just energy. It's energy going through the walls. It doesn't care how it gets through there. If it gets through there by condensing moisture on the outside of the tank or by temperature difference, right? So now you gotta ask yourself, well, what happens when the coil falls below the dew point temperature?
When it's running.
When it's running, right? What happens? It gets
It's
absorbed
absorbing
by
latent
heat
heat
energy
and
sensible heat.
sensible heat.
So if the latent heat gets really high, what do you notice with your suction pressure?
Goes up
Suction
higher.
pressure seems to be higher than normal, right?
Right.
So humidity does drive suction pressure,
Right.
Right.
You have load.
and when you have enough of it. So that's just some of the things we have to do. So, central air conditioning air source heat pumps, DOE did a study. 70 to 90% of homes have at least one fault. Here's, you can apply this right across commercial, it's the same thing, right? Commercial guys are in the same boat as residential guys are pretty much. So 70 to 90%, that number increased to 90 to 100% when the duct leakage is included. Poor installation may use 9% over ideal, 9% more energy. And then inadequate, the most common faults were namely inadequate refrigerant charge and insufficient evaporator airflow in 50 to 72% of central air conditioners and air source heat pumps. Fixing those two problems alone could reduce energy loads by 5 to 10%, right? So NIST, similar study, Vance Payne's a really good guy at NIST. I've met him before. We actually did some testing at NIST labs. Duct leakage, refrigerant undercharge, equipment sizing, low airflows, overcharge are the biggest problems. In Houston, just lowering the thermostat setting by 2 degrees Fahrenheit would increase your energy use by 20%. Think about that for a minute.
Yeah.
You drop the temperature in this space 2 degrees, you could get it comfortable in here, and it's gonna increase your energy use by 20%, all right? Because what happens with for a homeowner or a business owner, the only control that they have to interface with is the thermostat. If it's not comfortable, they're gonna turn it down further. Guess what happens? There's what's called a balance point, right? What's the balance point on a system? On any system, we have a balance point. What is it? Anybody know? Balance point is when the rate of heat absorption in the building is equal to the rate of heat rejection that the air conditioner is capable of doing, or a heat pump is the heat exits the building at the same rate we're putting it in. That's the balance point, right? You can have a balance point on either one. Once you,
But you're only at design conditions, right?
well, theoretically, but what if your air conditioner's got a dirty condenser, right? Now, your balance point just shifted. Because if you can't reject heat outside, how does it get back into the evaporator coil?
Just research through refrigerant.
Where does it come back in? What line? The heat that's not rejecting the condenser comes back in on what line?
Liquid line.
On the liquid line. Well, what temperature does the liquid line have to get down to? It has to get down to what? It goes to the metering device, gets down to what temperature?
40 degrees, say.
Saturation temperature of the evaporator coil, right? Whatever it is, okay? Here's the thing. On evaporator coil, the first liquid goes through, what's that called? As soon as it goes through the metering device, you have a
Flash
flash gas.
Your percentages,
So
your
now you're-
percentages are,
Your percentage goes up. So
Ratio.
typically we have 75% liquid, 25% vapor. Right now it's gonna shift and it might be 30 or 40% vapor, right? So what happens to your capacity of your air conditioner? If I gotta cool that warm liquid down and I have more of it go to flash gas, I don't have refrigerant.
the
in my
effective size
evaporator.
of your evaporator goes
Yeah,
down.
So it's gonna go down, right? So all of these things, when you start looking at equipment, you know, things you're gonna look at. Seriously, today, I want you guys to stop and think about something. This is where I keep seeing a problem in our industry. If 7 out of 10 systems have faults, 7 out of 10, that means if you walk up to a system today, there's 10 rooftops, 7 of them, you will find a pretty serious potential fault in it. 7 of them, 7 of them, right? Are you guys finding it that way or leaving it that way? Because if you're not finding problems in 7 out of 10 systems, you either got really good mechanics and there's stuff you guys take care of. But I'm telling you, if you go out on new jobs, I got my butt chewed by Greg Montali when I went out to BF Goodrich. We had to we had the, Be of Goodrich and Green, right? 19 rooftop units out there. I go out there and I call him up and I tell him I need like 16 belts, and I need all these filters, and I need economizer controls, I need all this stuff. I'm out there like for 2 days on this stuff, and I give him a laundry list of stuff, and he's like, "The hell are you doing? Well, we go out there and service that equipment all the time." It's just when I first hired in a gardener, I'm like, well, I don't know who's servicing it, but I'm telling you, there's problems. So they send out Mike Rendell out, and he comes out, and he's like, "I don't know what to tell you, Greg, he's right. You know, I had bad compressors. I had somebody change the compressor on, put a dryer in a liquid line dryer, the discharge line." Right? I'm like, that's not a muffler, you know. And so this is the kind of stuff. And the first time I'm going out there, I'm finding boatloads of problems. So eventually, they put me into a service manager position where I'm watching some of the younger guys. So I go out and I go out on a job site, and John Wilk, remember John Wilk?
Yeah.
So John's up there sitting in the mechanical room, and he's got the old check sheets that I have, and he's just copying down the readings off my check sheets and putting them on his. I said, "What the hell are you doing, man?" He goes, "Man, we're out here every quarter checking this stuff. It doesn't need checked." And he goes, "I want to learn this tracer stuff." He was doing it because he wanted. They had a tracer summit there, and he wanted to learn how tracer summit works. So he's like trying to. Nobody would teach him this, so he's like trying to save time over here to learn that. So I'm not like faulting the guy. I'm just telling this is the reality of what happens. I'm like, let's go up on the roof and look at this equipment and see how much of it doesn't need checked. Because it wasn't only John that was doing it, it was multiple people doing this stuff, right? And so part of what we use Measurequick for, and we're gonna get into this a little bit, part of what we use Measurequick for is to make sure when your guys go out to the jobs, that they're actually doing the damn job. And when you print that check sheet out and it's got all the readings on the check sheet that came off the tools, the geolocation and timestamp, it's like somebody actually did the work. Because somebody is paying to get that work done. Ultimately, it's a customer paying, but the boss is paying you guys to do the work. And if you guys aren't doing it, then it results in a callback, then it's gonna be a huge problem. Take over a company. Anybody guess what it costs? Now, this is a small company, right? You probably, what do you have, maybe 10 people?
10. Yeah.
All right, 10 people. Let's just say an average salary of $70,000 a year. So that's $700,000 in salaries, right? Is that right? 700,000 in salaries roughly, right? How many of those that $700,000 in salaries? How many of those people bring a dime into this company? None of them. They're all overhead, right? This building is all overhead, right? Offices are overhead. None of them bringing any money. Only people bringing in money are the service technicians in this company, right? So when you guys look at what a callback costs, a lot of guys just go with their wage. They go, "Oh, well, it's just costing 30, 40 bucks an hour." But there's the overhead cost. There is the cost of the technician. There's the opportunity loss because you're not there,
Yeah,
right?
something else.
You'll be making money somewhere else, right? And you think about overhead costs, there's cost of uniforms, cost of benefits, medical benefits, cost of your vacations, all that stuff rolls into play. So when you look at a typical company, anybody have a guess what a typical, and we get this from Service Titan, because they actually track revenue per ticket, revenue per tech, all this kind of stuff. Typical company, what it costs for a callback per hour. Anybody have a guess?
150,
300.
$400 to $700 per callback occurrence per hour, depending. Some of these residential shops, they charge quite a bit, okay? But $400 to $700 per hour because of all the overhead costs running a company. You sat down and you actually, a lot of companies this size, they're subsistence companies. The owners aren't making a ton of money. They might be making a decent living, but they're not bankrolling in cash every day. It's just reality of what it is. They're subsistence businesses. They keep everybody with an income. The owner makes a little bit more cash, but there's not a ton of extra cash here. And when you start throwing that money away on a callback, it costs the company a fortune. So when we're looking at one of the mentalities that I always try and teach with Measurequick is make your first customer your only customer in your head. Because I'm telling you, if you start really looking at equipment and really understanding what's going on, there's a lot of opportunity to be had in finding and fixing problems for your customer, right? So at the end of the story, the moral of the story here is nothing's more expensive than missed opportunity. So our vision with Measurequick was to get control of the problems and make money. If we could identify the problems on optimized equipment operation with Measurequick, then benchmark to restore the personality. We're gonna talk about that a little bit in the cloud. Or every single system has its own personality, right? You guys remember when you first got in the field and you're calling your lead tech, calling your dad, or calling whoever you could call that knew, and you're like, hey, what should the pressure be on this machine, right? They're like, I don't know, probably around 70 and 250, right? Somewhere around there. So when I worked for PK Wadsworth, somebody told me it should be around 70 pounds. I don't probably remember this. I overcharged every single piece of equipment I touched. Because if it didn't have 70 pounds of pressure when I got there, it was gonna have it when I left. So, once I got, 30 pounds of gas in a 5-ton system, and it was making all kinds of horrible noises, I decided that probably wasn't the best move. And then some kind of monitoring system, I'm not gonna cover too much of that tonight, but, so what we built was a diagnostic performance scan tools, sort of thing, a Measurequick. Like you have your car, you plug the scanner in, it makes the measurements, runs the diagnostic. That's exactly what Measurequick is, except we're doing the diagnostic with portable instrumentation, right? So here's the other thing I found out. Measurequick is like really a system. It's a measurement system. And I found a lot of people can't implement systems in place. It's like a big hurdle for a lot of people. In fact, one way to really tell if somebody's can put systems in place is you walk into a company. Now, if you guys have been in a couple different companies, you either notice that stuff's pretty neat, like this place is pretty neat. There's some organizational systems in place, some paperwork systems in place, where you walk into a company and shit's just piled up on the tables 2 foot deep, right? And about the only system they may have in place is the billing system, because they don't have that, they don't have cash in the door. But they don't have any way of organizing parts, they don't have any way of organizing trucks, they don't have any way of organizing anything else. And this was a process here, and I realized at some point this is my process, and so we're trying to teach people this process to get them through, getting the complete, getting the problems done, looking at the entire system. This is the other thing with Measurequick is it takes a system approach. We'll talk about that a little bit too. So, first of all, in our industry, we got to stop trying to fix everything at the appliance, right? When I say this, I'm serious about this. How many of you guys go out and do a rooftop inspection? You go out there with the jumper wires, you jump with the rooftop units, and you never walk downstairs in the building. You never look at the thermostats that control that piece of equipment. You never look at the registers, you never look at the returns, you never look in pop your head up in the attic and make sure stuff is connected or whatever, right? You're just up there, you service the equipment. Kent State Stark, I was up there working for, I don't know, probably 10 years, went back with Gardner, it's down in North Canton there. It has a hot deck, cold deck system, 40 volt electric reheat, it had 4 train chillers, 2 chillers with 4 compressors on them. Every time I went down there, all 4 compressors are running, walls to walls. Ran like that for years. Johnson Controls ripped out the inlet guide vanes on the fan, had a 90 horsepower blower. The inlet guide vanes started to go bad. Johnson Controls ripped them out. We don't need no inlet guide vanes, right? So finally I got Stark State let me go in there, and what was happening was, I noticed that like when I walked down the hallways, it was like a wind tunnel in the hallways. The whole building pressure was just screwed up everywhere you went. And the hot deck, cold deck boxes, the ducts were constantly blowing off the boxes. They just blow right off. Well, the thing was running 6 inches of static pressure. Wow. It was supposed to run, I think it was supposed to run 2 inches of static pressure. So finally got them to invest in a variable frequency drive. We put a drive on, we dropped it down from 60 hertz down to 30 hertz, maybe 35 hertz. Dropped the static pressure down from 6 inches down to 2 inches of static pressure. Chiller 1 shuts off. Chiller 2 shuts off. Chiller 3 shuts off. Chiller 4 goes run on the loaders on an 80 degree day, right? They saved so much money in that drive paid for itself probably in the first month and a half out there, right? But it was, and everybody at Gardner went out there and they would service the chillers, and they would put their gauges on, and they'd look at things, they measure superheat, they measure subcooling. And the chillers were running fine because they were running balls to walls. Nobody looked at the system, right? The main problem with the system was there's no inlet guide vanes. We had high static pressure in the ductwork. We had excessive amounts of airflow. It's blowing apart the ducts. It's totally pressurizing the building wrong, right? And this is the kind of stuff that if you start taking a system approach instead of trying to fix everything at the appliance will absolutely change the way you do work. Because it's not the appliances that have problems as much as it is the systems on there, right? Here's an example, right? Low suction pressure. right? That's a symptom, it's not a problem. Everybody says, oh, the problem's low suction pressure. No, it's probably low refrigerant charge, or it could be low airflow, restricted metering device, or restricted dryer, or low return air temperature, right? Humidifier bypass open, undersized evaporator, oversized condenser, plug filter, right? But nobody's gonna say, oh, suction pressure's low, let me turn up the suction pressure adjustment screw and get that where it belongs, right? We can't just turn that stuff up. So you gotta understand, when you see this low suction pressure on the machine, there should be a flag that there's something wrong. You don't obviously fix this by adding gas.
What gas in it?
What's that?
Gas.
Put gas in it, yeah, that's what this thing is, right? So, you know, adding charging is gonna fix low airflow issues, adjusting blower speeds, not gonna repair crushed ducts, turning the thermostat, it's not gonna cool it any faster. You know, I always see guys adding hard start components to the system. It's like, did you take a look at the wiring, right? That's a big pet peeve of mine. Every couple of years, you need to pull the panel off the system. And you need to shut off the breaker first. You need to check and see if the connections in the breaker are tight, right? Because the connections loosen up, because things get hot. Every time it starts, it pulls a lot of current. It loosens up the screws on the breaker. Then you need to go to the disconnect. You need to check the ones in the disconnect and out of the disconnect. Then you gotta go to the contactor and check the ones going in the contactor, right? Because loose wiring causes all kinds of problems. Lights flickering, problems with systems not starting, and it's all just big problems. Condensate lines, right? It's another big pet peeve of mine. How many times do you think I've cleaned my condensate line in 20 years in my house? Well,
Twice.
13 years in my house.
Twice.
Never needed to. Never ever need to. Nobody, what kind of water is it that goes down a condensate line? Distilled water. So anybody got a CPAP in here? Alright, so when you take your CPAP, you go to Acme and get a bottle of distilled water, you don't ever notice the dirt in the bottom of the distilled water? No, because it's not there, right? How the hell does the dirt get in a drain to make all this biological growth and everything else if there's no dirt in distilled water?
Filter bypass.
Filter bypass, right? Yeah, we see this stuff and somebody goes out, well, the problem's the plug condensate drain, I'll fix that, and they suck the condensate drain out, yet they don't do a root cause analysis of why did that thing get plugged in the first place, right?
The
Seriously, think
filter's
about it.
hanging 6 inches out the side of the slot and done.
Yeah, and that's exactly right, open return on the side of it, you know, we see that kind of stuff all the time. But these are bigger problems that people are overlooking because they're not doing it. Visual inspection, right?
Oh,
This is the most, Measurequick is a great tool, but nothing in our industry beats a good visual inspection. It's just all there is to it. It's the same thing when you're a doctor, when they walk in, they look at you and figure out if you're pale or you're cold and clammy or do you look okay?
yellow.
You know, what's wrong with you, right? So you gotta start thinking systems. And this is the biggest change in my mentality when I got into doing this for a living was, first of all, we have a control system, right? The most basic control system is just your thermostat, right? Now you can have a control system with safeties, and you can have other controls, but we got a control system, low voltage control system. We have an electrical system that provides electric to that unit. We have an air distribution system that distributes the air. We have an air filtration system that filters the air. We have a condensate disposal system that gets rid of the condensate. We have a sealed system that our refrigerant flows around in, right? And we have our outdoor and indoor equipment and, you know, any notes that would affect efficiency and capacity. But, right, what is the use of putting gauges on a machine if the damn condenser coil is plugged up with dirt? Right? You already know it's gonna have high pressure on there. Why would you ever do that, right? How many of you guys, if you went home tonight and your beer was warm when you got home, when the crack went open, your beer was warm, would run to the truck and get a set of piercing valves and check the charge in the refrigerator, right? Nobody would. First thing we do is make sure the door was closed and the kids didn't leave the door open, there's not milk carton blocking something, right? You might pull it out and clean underneath the condenser or whatever, but you're never gonna tap into a sealed system. It's the first thing that 90% of guys do in our industry is don't wanna hook gauges up to the system, because when we were in school, they said, your gauges are your most important tool, you know, and you gotta have gauges hooking up the system. It's like, bullshit. You don't have to have gauges up ever. You should never, ever hook gauges up to a system. That's a absolute last resort. I'd be like going to your doctor and he's gonna cut your chest open and look into your heart and see if your heart's beating and your lungs are good, right? It's an invasive to the system. Your hoses that you guys carry around, how many of you guys completely dock your hoses to your hose parks every time you're done with them? I mean, tighten them up tight, right? Why is that? What kind of oil flows through your hoses? POE. What's POE do when it gets around moisture? Sucks it in like a magnet, right? Guess what you're gonna do? You're gonna add charge to that system. You're running right past all that moisture, and guess what? Your refrigerant's super dry, so guess what it does? It just rips that moisture right out of your hose, and where's it put it at? In the system, right? Every time we're hooking gauges up to the system, and guess what? It doesn't even take refrigerant flow to get that moisture in there. If you have moisture in your hoses, it's gonna go right by vapor pressure, just like a sponge. It's gonna go straight out of your hose into that system. Right now, luckily we have a dryer on there, but that dryer does not have an infinite capacity. Eventually gets to the point where moisture goes in, moisture goes out. One of the big mistakes we make in our industry is we quit putting in sight glasses years ago because everybody thinks they're for checking for bubbles in the refrigerant. No, that's actually a moisture indicator. That eye in there was to tell us if the system was dry, right, or purple, or whatever it was. But back in the day, there was a company, I can't remember who it was, Brewer Garrett made a fortune off adding dryers and, I can't think it was Brewer Garrett. One of the mechanicals in town here, all they did was put dryers and sight glasses on things because all these systems were wet. Everything was wet. And they knew it, and they'd get these systems straightened out, and they would run like tops for a long time. But the other thing that we're talking about putting dryers in, I'm a big believer in putting a flare dryer in. I know that you can actually make a flare fitting because I made them, and they work, right? We use them on mini splits, and they can take up to 600 pounds of pressure. A good flare fitting, if you hydrostatic test it, is stronger than a brace, right? Why is a good reason to put a flare fitting on a dryer?
So you can change it.
So you can actually change it, pump it down and change the thing.
Valves on either side too.
And you can put valves on
And
your
you can
side
do it
too.
without putting heat to it, which.
There you go, that's the number one thing right there, because everybody wants to sweat a dryer out, and they push the moisture right back into the system, right? Everything, that's how they get dryers dry, is they actually heat them up and bake them to get the moisture out, then they cap them, and you're good to go.
I'm saying when you take it out, you're putting the moisture in.
Yeah, it's a desiccant, so when you heat it up,
Should you take one side off
cut it out, you always cut it out.
if you're not cutting it out? Should
No,
you
no,
raise one side?
If it's
the
close,
other?
if it's close coupled between a liquid line solenoid valve and a manual shut-off valve, and the manufacturer still makes stuff, well, I don't know if they still do, but
Yeah,
a lot of them like to make it that way, you didn't really have a choice.
you're cutting it out. There's just all there is to it.
Cut it out and then sweat the fittings out of the other
You
stuff.
gotta figure it out, yeah, because you do not wanna sweat a dry, it's just poor practice, right? There is no way to get moisture out of a POE oil with a vacuum pump. It's impossible. It bonds at a molecular level. The only way to get it out is with a desiccant dryer, that's it. So as soon as you heat the dryer up, you pushed all the moisture back in the system. You may as well not even take it out in the first place. If you're not gonna cut it out, just don't even take it out, because you're better off probably leaving the damn thing in there, right? All right, photo documentation section of Measurequick, right? There's a whole photo documentation. I'm a big believer in documenting your work and what you're doing, what you're seeing, what things need fixed on there, right? Number one problem I see in the industry today, this was big commercial buildings, I don't care where you're at, air leakage behind a thermostat, right? How many of you guys have gone home to your own home? It's like a 95-degree day. You walk in, you're like, damn, it's cold in here. You're thinking, oh, it's just convective air currents because it's cooling all the time. Where we get this shit in our head that we just explain everything away so we don't have to look at it, right? That's just the way our industry works. We just look at stuff, we come up with an explanation that sounds logical, we believe it, and we move on, right? Think about how many times you do that. How many times you woke up in the middle of the night, look, and you go, damn, did I really see what I thought I seen? You're like, oh man, I missed that. You know, my brain's going 24 hours a day with this stuff, right? If you walk into your house is cold, that's because you have a hot air coming in behind your thermostat. Your thermostat thinks it's 78. Your house is set at 74. The air temperature in your house is now 72 degrees because the thermostat's going, hey man, I'm hot in here, right? And it's overcooling your house. And it is cold in your house because it's actually way below temperature because you didn't take a little bit of thumb gum and plug behind that thermostat. Just recently, I had a guy call me on an inverter system. He's saying, I'm having all kinds of problems with humidity control. It's just ridiculous. And I'm like, you need to make sure you plug it behind your thermostat because the wall is an unconditioned space. And he had it communicating with a crawl space. And the guy took and he drilled now, not only is it a crawl space, but it is an unencapsulated crawl space, meaning there's no plastic, it's dirt floor, right, underneath the crawl space. Now, the guy goes to put the thermostat wire in, he uses an 1.25 bit, he drills a hole up to the floor joist, runs the thermostat down to the wall. He doesn't want to make a little tiny hole that he has to fish the wire through. He's gonna make a big honking hole in there. He's got supplier leakage, ductwork's done down, it's got supplier leakage, it's pressurizing the crawl space, and it's pushing the humid air right up through that thermostat chase. Literally, you could take a lighter and hold it out there, and you can see the flame bending out like this. I'm like, dude, you gotta plug that. First of all, you gotta get rid of your duct leakage. Second of all, you gotta plug that hole, because you're pressurizing your crawl space, and you're causing that humid air to come up the hole. So what's he do? I leave, he doesn't use thumb gum, he goes and gets a paper towel, he gets it wet, he makes it into a spitball, and he packs it in the hole. Right, and he calls me back and goes, it still doesn't freaking work, and the humidity's through the roof. I'm like, did you plug with thumb gum? He goes, no, I used a wet paper towel. He goes, but it should be dry now. I'm like, that's not a vapor barrier, right? Paper towels, moisture will go right through that. You gotta put a vapor barrier in there, and that's what I told you to use thumb gum for. So temperature swings cause excessive run times, incorrect temperature humidity readings, you ought to plug it with thumb gum on there. Right, again, maintenance issues. Look at the condenser coil. You guys have all seen train condensers, especially the split ones where it gets so packed in between the coils, right? Condenser fan blades improperly pitched, positioned incorrectly. How many times I've seen guys put a new condenser fan motor in, and if you don't, you guys know what a volute is, right? So there's the center of the hole that the fan resides in. It's got to sort of ride the center of that volute. Otherwise, the air is going to go through the fan improperly, and you're going to get high head pressure. Electrical system issues, excessive voltage drops across conduit. There's no standard for this, but when you start seeing the contacts look pitted like this, they're probably due to be replaced. Dirty condensers, capacitors, those kind of problems. There's two pictures here. This is a real job I went on out in Memphis, Tennessee. Company called me out. They're like, hey, why don't you come out and give us a demo of Measurequick? I'm like, okay, I'll come out and show you how it works. And we're gonna take you to the field and have you look at a few jobs with our guys. They don't tell me they're taking me to every job they can't freaking figure out, right? I go into a lady's house. It's a historical home, right? Beautiful house, hardwood floors, antiques everywhere. She's got 2 dehumidifiers running on the first floor of her house, right? This is a picture from her house, and so they have a 4-ton and a 4-ton downstairs and a 3-ton unit upstairs, and about 2,000 square foot of home. I'm like, did anybody do a heat loss calculation in here? And they go, no, we just had an upstairs unit, downstairs unit. I'm like, well, let's take a look. So the upstairs unit's in an attic, so I get in the attic. I'm like, do you have any, it felt like duct leakage in the attic, because I could feel the pressure difference between the attic and I'm like, I think you got duct leakage up here, pretty serious duct leakage. Like, no. I start poking around, I find a hole in the return. I can put my hand down in, so we tape that up. And I'm up there, and I'm like, well, Measurequick's saying you got really high airflow. And he's like, no. He goes, we checked the airflow. In fact, it's set at 350 CFM a ton. I'm like, well, I'm telling you, software doesn't lie. You got high airflow. And he's like, I don't think so. And I'm like, well, I'll tell you what, let me just check your dip switch settings, ECM motor. So I go in there, sure said he's got it set for 350 CFM per ton, and 3-ton condenser, but they never changed the blower speed. It's set for 5 tons from the factory. So they're running 350 CFM per ton on a 5-ton system, right? 5-ton drive. It's pulling 0.9 gallons per hour of moisture out of the house. I flipped the dip switch down to 3 tons, restart the furnace. It went from 0.9 to 19 gallons, or 19 pounds per hour of water, about 2 gallons, a little over 2 gallons of moisture per hour pulling out of this thing. I'm up there explaining to guys what we're looking at, what we're doing, and the lady screams from upstairs, what the hell did you guys do down there? I said, was something wrong? I'm thinking maybe we're like leaking condensate or something because we're pulling out so much moisture. She goes, my dehumidifier shut off. They never shut off. And so, this kind of stuff, this was down in her crawl space. So then we go down to the downstairs unit. I'm like, I just walked down there and I'm putting my hand in front of the registers. I'm like, did you guys ever check the air coming out of the registers? And they're like, well, no, we don't want to walk around the house. I'm like, well, you're having problems with cooling the house. Don't you think you should really check and see how much air you got coming out of the registers? They go, well, they're fine. We put the ductwork in. They had a company come in and insulate the house. The insulators pulled the ductwork down to get the insulation bats up behind it and choked off their ductwork, right? Now they had 9 service techs out on this thing, and nobody went down and looked in the crawl space to see what the ductwork looked like. Nobody walked over and felt the air coming out of the register. They tried to solve everything at the equipment, right? And then this was excessive flex duct length. This is the most common problem we see, is these guys, I'm not kidding you, I went to a job in Texas, and there's, every single run had 25-foot flex duct. And one run had the flex duct box open at this end, and opened at this end, and connected, because it was only about 6 foot long. His boss told him he did not want to see, he goes, they paid for, there's 25 runs, there's 25 boxes of flex duct, I don't want to see any of this shit come back to the shop, use it all. And then, he told him that the system was proportional balancing if he kept all the runs the same. This is not a lie, this poor kid, we pulled out, I don't know how many feet of flex duct out of this job, and got the airflows where it should be. And that excessive flex duct length also has a lot of thermal gain with that. So they're losing all the cooling that they had in this house into the duct system, right? Pull and sit down, you see the homemade transitions, no mastic, right? This is a telltale. When you walk into this space, right? I always used to make a mental note. When I walk down here, I look for the thermostat, I see what the thermostat is. So in this case, it's 72. I go upstairs and I measure, or in my furnace room or whatever, and I measure 78-degree return air, right? That's a pretty good sign of what? Duct leakage. You're pulling hot air from somewhere. Whatever the thermostat temperature, if this is 72 at the thermostat, it should say 72 degrees in the return air, right? It should be exactly the same temperature, right? If it's hotter, that means you're getting duct leakage from somewhere, right? That's gonna erode your system operation. Oops, went back a slide. Another problem we see in residential, top plate leakage, right? Discolored insulation in the attic and things like that. And again, this is all visual inspection. This is before you ever hook Measurequick up to a system. You need to be going through, I don't care if it's commercial, industrial, residential, whatever you're looking at. This is another one in Memphis, Tennessee that we went to. Honest to God, this is nine guys out for these jobs plus. They cannot find the problem with the job. I'm like, what's the duct system look like in the attic? I don't know, I haven't gone up there. Equipment's not running right though. I'm like, maybe your equipment's fine. Pop up in the attic, here's what we find. Flex duct is literally all of it's fillet of duct, right? It's falling apart.
120 degree.
Insulation breakdown, limited life. Restricted pleated filters, this is another one that we see a lot, especially with COVID right now. Everybody's going out and buying a 3M, nothing gets through this filter, including air, right? You may as well leave the plastic on because it's about that restrictive. This is one in my shop, I just put a 3M filter in there, and it was 0.29 inches of static pressure drop across the filter. Took the filter out and blocked it with paper, right? So no air is getting through the paper. So that's my effective grill area right there with that filter in, because the pressure drop is so high. Right? Now, when you're using Measurequick, we test from inlet to outlet. So when you're looking at this here, we always want to put the probe on a filter grill and on the closest supply. I know that's not possible in every situation, like some rooftop systems we can't get the stuff up top where it needs to go, but this is the way the software is designed. Let me explain why. If I have 70-degree air going in there, right? That 70-degree air is that is the driver for my suction pressure, correct? On my machine. Everybody agree with that? So if I have 75-degree air going into the equipment, and this is what happens a lot of times. Guys, you go up, you put a probe up in the equipment, it'll be 75 degrees, and you adjust the blower down to get a 20-degree split, right? You adjust it down, you go, oh, the split's no good, I'm gonna get a 20-degree split off this thing. You can measure what was coming into the return, it was 70 degrees, and figured out you had 200 CFM leakage into the return air duct. You realize that turning that blower speed down isn't fixing the damn problem. You just got the split right, but now you haven't taken care of the duct leakage, right? This is a very common problem in our industry. So Measurequick will actually pick up that duct leakage. And this could be the same thing if you have a economizer leakage. Doesn't matter, right? It's the exact same thing. If you're putting your probes in the wrong location and you're not taking into account your mixed air temperature in there, you're missing opportunities there, you're missing problems. I got on there. Condensate drains, when you start seeing this stuff here, that condensate should be clear. That's the same thing with natural gas condensate. If you're on a condensing appliance, it's not dirty either, right? We don't have dirty water coming out of that. When you start seeing that dirty there, we're getting dirt bypass the filter or something's wrong with combustion. These are flags you guys need to be looking for, right? Caps missing, indoor evaporator coil starting to foul. This causes a huge amount of problems. Air bypassing, this is the bottom of an evaporator coil. The guy put it up on slips and drives and 1 inch gap on the one side of the coil. Air's not going through that coil, air's gonna go around it. As soon as the coil gets wet, all this cooling's bypassing the coil, right? This is another one we're seeing a lot. You guys hear about the big ass drop, guys are putting this like 20 by 25, 20 by 20 drops on residential equipment now to get the air velocity, bigger filters, get the air velocity down, right? So walk in, the job, guy's got a big drop on the furnace, and looking at everything, I'm like, wow, it's a nice looking duct system. So I put a static pressure probe in there, and it's drawing like 7/10 of an inch of static on the return. I'm thinking, wow, the filter must be plugged solid in this thing. I pull the filter out, it's still running 7/10 of an inch of static. I lost like 0.05 inches on my filter. The filter was fine. The filter's not even dirty at all, right?
You lost your velocity.
No, it wasn't that. It was that he had this pan that went to a double 2x10. And then it went down, and it went down a wall chaser with a 2x4 wall. So literally went from a 20 by 20 duct into two 2x10, joist panned over, up into a 2x4 wall space and a filter grill, right? This is the kind of stuff, if you don't look at the system, if you don't chase it from one end to the other, you're gonna miss it. If we're not measuring the vitals, like things like static pressure, we're gonna miss it. And that's a big problem. So the quick fixes here, the most low-hanging fruit in our industry: dirty condensers, duct leakage, highly restricted filters, air bypassing the filters leading to dirt, dirty evaporator coils, refrigerant charge, fan speeds, high statics, trapped air leakage, another big problem we have. You see this a lot on rooftops where you got a draw through system and your traps are not big enough. They're using an undersized trap. You're just pulling 1 inch air through there, or you're not draining the water and re-evaporating the water back into the space, right? A lot of these things aren't big expense. Let's talk about optimizing. So once we've done our visual inspection, we made sure everything looks right. Now, the whole key to getting efficiency and capacity out of a machine is the balance of airflow and charge. Right? You've got to have correct airflow, you've got to have correct charge, or it's not gonna work. Okay? So we're gonna start the system up. At this point with Measurequick, so we've done our visual inspection, right? Everything looks good. We're gonna turn the system down, and we're gonna start deploying probes, and we're gonna start gathering customer information about the system while it's stabilizing. I've been using Measurequick for, I don't know, 4 or 5 years now. I go out with guys all the time, and I'm like, here, I just want you to watch me do a test, because guys get out there and say, oh, it takes too long to do all this stuff. I'm like, dude, it takes 20 minutes for the equipment to stabilize. I'll have, by the time I'm done getting all the information and deploying the probes, I'll have the diagnostic done and I'll tell you what the capacity is, and we'll be done with this job. It's either running right or we gotta figure out what's wrong with it. And it's all about just learning how to use the system. So the deployment of the probes is the most important thing, right? High and low pressure, just where you normally expect them. Suction line temperature near the service valve, right? At least 6 to 10 inches away from the compressor. Why can't we be right close to the compressor? Heat, right? Heat. Here's the interesting thing. A lot of guys, I had a guy tell me the other day, I'm like, dude, you cannot put your probe that close to the evaporator coil. And he's like, why not? He goes, here, you put it on the backside, he's measuring air going into the evaporator coil. I'm like, it's going to influence the temperature. He goes, oh, bullshit. He goes, the air's going this way. I'm like, dude, have you ever heard of radiation, right? Radiant cooling. Heat travels from hot to cold, period. Your probe, your hot probe is going to see that cold coil, and it's going to heat's going to travel right into that probe. Doesn't care which way the air is flowing. It's going to cool that probe off because it's next to it. Just like walking in a freezer aisle at Walmart, right? You walk in there, you start feeling cold because you have all these open cases that are cold, and it's sucking the heat out of your body, right? Heat is radiant energy, so we need to be far enough away from the compressor we're not picking up heat. We need to be at the liquid line near the service valve. Discharge line, again, 6 to 10 inches away from the compressor. Return air wet bulb and dry bulb at the return air grill. Supply air at the closest supply. Outdoor air out of line of the sun. And electrical, we always measure incoming power. So again, probe placement, right? You see here, we want to try and avoid this. I know we a lot of times want to measure there because it's convenient. But again, if you're going to measure there, then pay attention to what this says. There's a 72 here and a 75 here. There's a flag, there's a problem going on. If you don't walk downstairs and check the thermostat, you're always using your jumper wires, you're going to miss this problem. Now, it could be the thermostat's out of calibration too. You can check that against your probe and make sure the thermostat's right. So, but it could be a problem. All right? Position the indoor probes. We're going to measure at the return air grill and the closest supply. If your capacity is low, here's what happens on a machine. I'm measuring 70-degree return air, got 55-degree air coming out, 75-degree air going in, though at the mixed air temperature, right? Now, let me show you what happens here. Here's two systems. This is measured at the equipment. Okay, so all I did literally was just take a probe from the return air inlet at the equipment and just moved it to the grill. Okay, this is literally all we did. 75-degree air, 50% relative humidity. At the equipment, I'm running 13.5 SEER. Sucker's running great, running 33,000 BTUs of cooling, 23,000 sensible, 9,000 latent. That equipment's running great, right? That's everything's running perfect. You just move that probe down into the house. It's now 70 degrees in the house. Humidity's the same. We're picking up sensible heat, right? This was all sensible heat gain due to uninsulated return air chase in the attic. So somebody handed it over, but nobody insulated it. So it's just picking up heat. That's all it is. No, and the humidity in there, I can't remember why it stayed 50, because it normally would have dropped down. It may have had some other leakage in here, but here's all I want you to see. That 36,000 BTUs dropped down to 24,000 BTUs, and we went from 13 to 10 on this here.
Right, the unit's running fine with the system.
So the system sucks. This is why we gotta take a systems approach and not an equipment approach, because you guys are going up and you're checking equipment, equipment's perfect. But your customer's losing a third of their cooling because of duct leakage, right? They're losing a third of their cooling because the economizer's leaking. How many, when I started in this industry, nobody taught me what an economizer was or how it worked. I mean, they told me I brought an outdoor air and stuff, but I really didn't understand how economizers actually did what they did. I didn't really understand that, some guys would tell me, so how much outdoor air should we bring in for ventilation? They're like, oh, just put 2 fingers in there, about that far, or whatever, And it's like, they're opposed parallel blades, right? So when you crack that damper open, about 10 to 15%, it's effectively 100% open, right? So those dampers are not, it's not a proportional, it's very, very small opening to get a lot of air into space. Gotta figure too, there's no restriction on an economizer, it's literally right next to the freaking fan, right? Your duct system may go down and go into a T and have filters and registers, highly restrictive, and then you got this economizer is literally open right next to your fan. It's got no static pressure resistance to it. So a very small opening is going to bring in a huge amount of air, right? So this is the kind of stuff, if you're not testing the entire system, that you're going to miss on there. Duct leakage accounts for the highest energy losses in the system. If you put it with Measurequick, what you can do is you can actually, if we have a duct leakage test, you can put a return air door. No, you don't need that. You just use 3 psychrometers. So you're going to have 1 psychrometer at the return air inlet, and you got to put 1 on each side of the blower. Why is this? Somebody tell me why. What happens when you have have you guys ever experienced duct leakage before in a system that you know of? How does air flow in a duct? If I were to take, this is an interesting thing, I did not realize this until I was at Cuyahoga Valley Career Center, and one day I decided, you know what, I'm going to screw with my students, so I had all my furnaces, I always believed in having ducted systems. And how many of you guys went to trade school? Right? Well, most of you guys did, okay. How many of you guys had duct systems on your systems at the trade school? We did. You must have went to McKim or something. Yeah. So, what's that? West side. West side. So, most of the time, like if you went to the Cuyahoga Valley Career Center in the 1970s, 1980s, there was no duct system. It was an appliance repair class. Because they never showed you a duct system on. In fact, I had to call my dad the first time I expected a heat exchanger, and I'm like, Dad, there's duct work on top. How can I can't even see it. Because I always thought you expected it from the outside. I never realized there's a coil on top of it. I was screwed, right? And it's literally, nobody taught me. And I actually went to state competition at Career Center. But I wasn't stupid or anything. My instructor didn't teach the way that things need to be taught. Now, going back to this is just mixed air formula. So you have a return air dry bulb, you have mixed air on each side. Now, this is where I'm going back to, I put duct systems on, and I said, well, I'm gonna pipe hot air from one of my furnaces right into return, just to simulate attic leakage, right? So kids go over there, and I'm expecting to turn on the furnace, they're running it, puts the probe in the return air grill, and it's reading 72 degrees, right? I'm going, damn it, my furnace must have shut off. I walk over there, it's got 140 degree air. I put my hand in the duct and it's hot as hell. Go back over and say, well, the damn thermometer's screwed up. And couldn't understand what the hell was going on, because I envisioned in my head that that stream of air was just gonna shoot across that duct, it was gonna mix in, and I was gonna get this warm mixed air temperature. That stream of air just went right down the backside of that duct, straight as could go, and it only went out about 6 inches, the width of the supply duct. So what it told me was, measuring in return here didn't show me what was happening over here. Now, when the air goes into a fan, into the flute, it's turning and spiraling. So if you put
It gets mixed.
a
but also
micrometer,
gets heat added to it.
yep,
For the moment.
but what is crazy is, and this is, guys will go out and they'll say, in an air conditioning system, you get high, you know, you can have higher temperature over here than you can have over here. It's like, what they don't realize is that you can actually pull hot air into one side of the fan, and it'll discharge out that side of the fan hot, and it'll literally, when it goes in, and you think about the center of a fan, it's got a plate in the middle. It'll actually have two, when it goes in hot one side, it'll come out hot the other side. You'll have a hot half your coil and a wet half your coil. You ever seen a coil load up funny where half of it's covered with dirt and half of it's spotless? That's because the coil's not getting to even temperature. Yeah, half of it's dry, it's not rinsing the dirt off. It should have never got there because the filter was blocked, right? So you put 2 mixed air probes in, one on each side, and then you measure the attic here, and it measures the static pressure. Now, going back to, you mentioned a duct leakage test, so we typically test ducts at 25 pascals. And so what Measurequick does, it calculates total capacity loss and then the duct leakage. Now, when you input the nominal tons, the length of the run, the size of the ducts, this in the R value insulation, this additional information tells us how much capacity loss we have due to heat gain, and how much capacity loss we have due to duct leakage, right? So it's all built into the software to do that. So this is where you have return air, supply air, mixed air, attic air, right? This is times 2 probes on there, okay? Another big problem, and especially on the residential side, but this can happen on the commercial side as well, is we're not paying attention to what's next to our returns, right? Now, I've done this before. I've gone up to pop my head up to a ceiling, and you go up the ceiling, you know it's hot as hell up in the ceiling because it's unconditioned space right above you. And all of a sudden, you're doing something up in the ceiling, you're not realizing that you're affecting the equipment operation because you got hot air coming right out of that ceiling and going right in that return, right? This is exactly what's happening right here, is we're depressurizing the zone. Now, here's something I want you to think about for a minute. I can take a candle and light it on that table. I can blow air through the candle and blow that candle right out. I can blow air across the room, okay? But if I stood the same distance away and tried to suck that candle out, I can't do it. Because it creates an area of low pressure, and the room pressure will immediately expand and fill that void where I pulled that air out. So you cannot pull air, you cannot suck air across the room. In fact, this was something we learned when we designed our filtering system for our office. Actually, you put a high velocity system across the wall over here, so I can throw air clear across the room. When I throw air across the room in streams of air, guess what happens? The air around here, it actually gets entrained. When it's blowing through, it creates entrainment, and I'll pull the air back and I put my 2 filters in the back. So I have my returns in each corner and my supplies right in the middle here. And so all my ductwork's on the same side of the room, right? Completely counterintuitive to what you might think. But I got my particulates down to nothing in my room, in my space, because now I'm actually creating an environment where I can blow air out and return it back to those returns. Otherwise, like in here, the only thing that's going up in the returns in here is what happens to be in the air, whatever particles are in the air. You cannot suck dust particles to that return. You have to create an area of entrainment to get those back. So it's just one of the challenges we have in the system. So air side corrective measures, you know, we need to be looking at things like cleaning the blower, cleaning the evaporator, less restricted filters, supply air grills, additional returns. Got a company in California. They've increased their revenues somewhere between 40 and 60%. One of the number 1 things they do is add additional return air grills and systems. You're gonna find the same thing. Most commercial systems have undersized filter grills, undersized returns, right? And just going in and adding in an additional return air in rooms and things like that, getting these rooms balanced is gonna make a big, big difference. And how many times, anybody ever worked in a place like Cuyahoga Valley Career Center? It's had like 7,000 remodels, right? You guys have been in those buildings. You got, 75 foot of flex duct, and it literally goes out, moves around, and comes back, right? nobody's gone in and retro commissioned the systems, the guys came in and they just threw up a new ceiling and they put the registers wherever, but fix that outside of the unit, you would be missing some opportunities there. Right, turning vanes, larger wire ducts, grills, dampers, evaporator coils, anything you might need to fix that. And most of you guys done all your charge related stuff here, you have overcharge, undercharge, and non-condensables. That's non-condensables, most common problem. Just had a contractor, Cortland Partners, they went out, they were gonna acquire 1,000 unit property. They're a property management company, right? So they buy all these little apartments and things. Went out and did a survey with Measurequick. They surveyed 80 apartments. And typical cooling capacity was at somewhere between 40 and 57% of the rated capacity in machines. They found out that the contractor went out and did the startup, never did 1,000 units, never did an evacuation on a single unit. What? They did not have power at the unit, and he didn't even give them the courtesy of a blow and go, blow all the try and blow all the air out of the line set. He just opened up the service valves. So the systems were full of air. They ran for several months like this, and they called me up and they're like, what do you think we should do? I'm like, I wouldn't buy the property or get them to change out the entire systems because the systems are absolutely ruined. They're like, line sets too, and I'm like, everything. Because now that line set's coated with oil, everything's wet. With multiple dryer changes, it's gonna be a nightmare to get this property fixed. Right, so I don't know what they're doing with the property now. It's a disaster. Right? They still ended up buying it, but this is the kind of things that we got to watch for. Measurequick, when you're running a scan here tool, it does have a flag at the upper top. If you touch that flag, it's going to pull up what's major potential faults. Now I want you to notice the verbiage in here. It says condenser may be dirty. Measurequick was never designed to replace a technician. I can't tell if your condenser's dirty or not through software because you could also have an overcharged refrigerant. In fact, in this system, that little 2 next to flag means there's 2 symptoms of that, or 2 symptoms of an overcharge, right? So I could have high head pressure and I could have high subcooling. You go, well, how the hell does high head pressure cause high subcooling, right? Well, if you have a low ambient temperature and you have a big condenser coil, what is the coldest the liquid line temperature can get to? What's cooling down a condenser? Outdoor air, right? So the coldest the liquid can get is to the outdoor air temperature, right? So if you have a giant condenser, it's going to get down to the outdoor air temperature every time on a mild day. But guess what's going to be higher when you have a dirty condenser? The liquid temperature is going to be the same, but what's going to go up? What'll go up? We have a dirty condenser, we're not rejecting the heat. The liquid's getting down to temp, but what's going up? Head pressure. So we have an increase in head pressure that results in also an increase in condensing temperature. Increase in temp, if we have the liquid line temperature stays the same, we increase the pressure, guess what we get? Artificially high subcooling. Right? So what's the first thing somebody's going to do? They're not going to look at the condenser, they're going to start dumping gas out of the machine. Oh, it's overcharged. It's like, did you look at the condenser? You just split it apart and see if it's dirty in between, right? Because this is the kind of stuff people do all the time, and they figure somebody just overcharged it without taking a look to see if it's actually dirty. So when it says their condenser may be dirty, that means you need to look at it. Or it could have an overcharge, or it could be a restriction of liquid line, right? If you tap on that, any of these targets, it'll tell you what the current value is, what the design target is, and the ideal range. These two don't match up. I didn't realize it when I made the slide here. But whenever you see what WTF, right? What's the fault? You need to run diagnostics. Okay, whenever you see the flag, right? Faults are probability based. So this is actually something that we do that's pretty cool that nobody else in the industry has figured out. Is that we use what's called the Bayesian mathematical model, and basically Bayesian is part mathematical and part common sense, right? So when you look at this, the odds, if you look at how these both scored a 2, but the condenser is scoring higher, it's higher on the fault because the odds are higher that you have a dirty condenser than you have a refrigerant overcharge, right? If you looked at all the faults in our industry, which right now, like I just looked at the other day, I pulled down somewhere around 60,000 records out of Measurequick. I have data on every system in the country that people use Measurequick on, and what I do with it is I go through and I start to look at how systems are running so I can make our software better, right? And a lot of it's all done by hand because I don't have artificial intelligence to do this. I got to use my own, right? So we go through and look at where they're having charge problems, where they're having ductwork problems, and we start making these faults pop up.
Hey, Jim?
Yes?
Before, can you go back to that slide?
Yep.
So that was one of the questions that I had. That probability score then is actually how many symptoms are saying. that
Yeah,
that's
so if you click on
probably-
this
'cause I've
minor
seen
faults,
I was wondering what the range was, cause I saw as high as a 6 on something, I think it was low charge or something.
yeah, so that's 6 symptoms of.
6 symptoms, so that's the number of symptoms telling you that that's,
Yeah, and some of them are a little
Possibly
weighted,
what
so
it
it
is.
could be, sometimes we rate some symptoms a little bit higher, so it could be, but it's, in general, it would be 6 symptoms of low charge. So it could be like low suction pressure, high superheat, low head pressure, maybe a high approach, and then, low, capacity,
Delta T.
right? Or low delta T, so everything that we measure, with the exception of very few things, has a target in Measurequick, right? So we're actually calculating what your suction pressure should be, your head pressure should be, what your suction line, your superheat, your subcooling will be. They're all driven by, and think about what drives the return air temperature, or what drives the suction pressure is your return air temp and your relative humidity. What drives your head pressure is your outdoor air temp and your relative humidity, but not the way you think. It's the relative humidity that's absorbed in the evaporator
right,
that drives the head pressure, right? Not the relative humidity outside, because what's the difference between the indoor coil and the outdoor coil? The indoor coil does what? Removes 2 things, heat and humidity. So it's, in the outdoor coil, we're rejecting all that humidity, or all that moisture we absorbed and drain down the drain, all the heat that required, we're rejecting as sensible heat.
so when you're using this, you're saying you can't use it while it's raining?
Can't
The
check your
outdoor
system.
coil's wet?
No, the coil's wet, it's evaporated cooler, right? A lot of guys want you to do that, but here's the thing, okay? A lot of guys say you can't work when it's raining out. Well, you can wash the condenser when it's raining out. You can change the filters when it's raining out. You can't check the charge when it's raining out. But there's a lot of other things you could be doing. You could be going down and pulling the stat off the wall, see if the hole behind the stat's plugged. You can be popping your head up and seeing what the ductwork looks like, making sure the ductwork's actually connected to the returns and to the supplies, right? Making sure fire dampers are open on the duct system. Going out, how many of you guys have walked into a room and actually reached up and felt that the air's coming out of the registers, right? It's just stupid stuff. People are hot in offices and uncomfortable all the time because nobody's taken a few minutes to go downstairs and actually check the air delivery system on there. So here's just a visual, and I got so screwed up with this when I was in school, but I want to make sure that we get this down tonight. When you're looking at a refrigeration system, there's just a liquid seal at the bottom of the condenser, right? I always got in my head, I was thinking the condenser was full of liquid. You know, if somebody told me the condenser's where the liquid's at, the evaporator's where the vapor's at, I'm like, okay, well, the evaporator is almost full to the top of the liquid. Just the very, very top of it's a little bit of vapor. And all the vapors in the condenser it's actually raining in there. It's de-superheating, saturating, and subcooling to liquid, okay? So when you go outside, here's the interesting thing with air conditioning systems, right? Have you guys ever gone out, you start the system up, you see the suction pressure just tank, right? Just tanks down. And then it slowly creeps back up again. When that happens, where do you think all your refrigerant's sitting?
It's in the evap, 'cause that's where it was cold when it shut down.
Not in the evap,
Condenser.
in the condenser. If it drops down there, if the pressure drops on the low side, there's no refrigerant in the evaporator, because it's starving, it's just starving. And so what happened is all your refrigerant migrated in your condensers. Think about like when
Oh,
go
when
out
it's cold
and
outside more.
it's cold outside, all the refrigerant migrates into the condenser, you gotta start it up, and you don't have anything for your evaporator, and it tanks, right? In the summertime, it's cooler indoors than it is outside, and all your refrigerant migrate into the evaporator where you want it. And the system will start up and run really quick, it'll get up to operating temp. So this is why, when you go outside when it's cold, and you're trying to do a cool weather inspection, it's really hard because all the refrigerant's in the wrong place in the system, and it takes a long time to get all that refrigerant through that condenser, through that little tiny metering device hole, and up into the evaporator where it goes and stabilizes. So it takes time for that refrigerant to balance in the system. We're always chasing that refrigerant around in that system, right? So benchmarking, once we get this system right, once we have the airflow set, we have the superheat correct, we have the condenser correct, we're gonna benchmark the system. It's gonna capture the personality. Now here's a key thing with that. Let's say you got 2 10-ton systems, splits, right? One of them pokes through, it's got a 20-foot line set, pokes through the wall, goes to an air handler in a basement. The other one goes up, it's 150-foot of line set, trapped, goes up, goes across the roof to a condenser on the far side, maybe 150-foot long, right? Huge long line set on the one machine, short line set on the other. right? We got two different duct systems on those systems. Even though it's identical equipment, they're gonna operate differently.
Personalities.
They're gonna have different personalities, right? Because there's gonna be a drop in suction pressure in that suction line because of the length of the suction line, right? Hopefully it's not more than 3 pounds. Hopefully somebody sized the line correctly, but that's not always the case.
Even if it's insulated, if it's going through a hot attic or across a roof.
Across the roof, it's gonna pick up additional superheat, right? Important thing to remember, the TXV cannot control superheat after the thermostatic expansion valve, right? A lot of guys, and this was a half-day Gardner train, what was the name of the high school? It was out in Maslin. Can't remember. That's right tip of my tongue. I go up there and find out there's been like 7 compressor changes on a machine. And I'm like, what the hell's going on? There's gotta be something wrong with this thing. So I started digging into it because I'm noticing that I'm getting just a crap load of oil back on the compressor. And thinking, well, a lot of compressor changes, maybe gotta drain some oil out because maybe the oil was washed down the evaporator and just never got back up. I don't know why it was returning that day, but it was. So I go downstairs and I try and measure the superheat of the evaporator. Just, it's got an external equalizer line, connect the external equalizer to get the pressure, go over and measure the temperature. I'm like, I got no superheat. In fact, I fill the suction line and the suction line's warm. I go back upstairs and I measure it upstairs and I'm like, it's like around 12 degrees of superheat. I'm like, how the hell am I getting superheat upstairs but not downstairs at the unit? And well, ended up that they told him, well, you gotta have 12 degrees of superheat at the compressor. So the guy just kept opening up the thermostatic expansion valve, opened it up so far that it was no longer metering anything. And all the refrigerant was flashing in the suction line. So instead of flashing the evaporator, it's producing no cooling, and it's flashing in the suction line, huge long suction line. So I start cranking down that TXV on that thing till I get the superheat at the evaporator coil. And I'm picking up a lot of superheat up to the compressor, right? Now I'm running like, I don't know, 20, 30 degrees of superheat at the compressor. The answer was just, insulate the suction line, right? Because somebody had run it through and nobody put enough, it was under insulated in a lot of spots, missing insulation.
Or buried underground.
Well, anything, like water will do that too, you'll see all of that. But it goes back to testing the system. Now, what we wanna do is when we get the system done, we're gonna benchmark it.
So the cause of the compressor failure was getting inadequate cooling on the compressor?
It was flooding. They were flooding because it was the the suction line does not absorb enough heat to flash all the refrigerant away. So on hot days,
Slowly washing it out.
yeah, on hot days it was okay, but on cold days it was not working. And what's crazy is there's no delta T on the evaporator coil. If you measure the supply and return air temperature, no delta T. And once we cranked that thing down, it was running, a 16, 18 degree split across it, and it was fine. All right, so we're gonna benchmark that system. What this is gonna do is Measurequick, when you benchmark it, it locks in your design temperature difference for your evaporator, your condensing temp over ambient, CTOA, how much hotter is the condenser than the outdoor air, how much colder is the evaporator and return air. Those things do not change. Your superheat, if it's a TXV, your superheat will remain the same at the evaporator outlet. That's the TXV's job is to maintain constant superheat. Now at the inlet to the condenser where we're looking to measure, we allow from 6 to 24 degrees of superheat as long as the suction line is below what temperature? 65 degrees. You gotta have a suction line below 65 degrees. We're gonna get inadequate compressor cooling.
It's an automatic black flag, isn't it?
It's an automatic black flag, yeah, except, here's what you gotta understand. If you have 85 degrees in the space, you're gonna have a 65, 70 degree suction line. It's not that we can't have a 70 degree suction line, we just can't run there forever, okay? In a short amount of time, it's not gonna kill anything. Runs like that for a long time, it's gonna do that. So we're gonna use non-invasive going forward. So what we're doing here is gonna optimize the operation. So you get everything in target zones, you get your tonnage correct, verify your capacity. Down at the bottom there's a benchmark button. And all that does is it locks these targets in. So you can see there, the pressures aren't exactly under the flags and things here, it's gonna lock this in. Now we just made a little change in Measurequick. You notice the target zones are a lot bigger now. There's 2 settings in there I can actually hook up. I'll show you in just a second here. In fact, let me just switch over for just a minute. In there, switch here.
Jim, do you want me to get the probe set up on the rooftop?
We can, yeah, we can just do that if you want.
Well, while you're doing this, I can do that, so
All right, you got, my probes are out there, did you,
I have it right there.
yeah, why don't you just use those, because they're already mapped to my system. This one is, this is outdoor air, and, this is return air, and then this one is, this is supply. You need hands on? She's certified. You need a hand? Check his credentials.
I don't know.
He said, Brian, I come here. What was the deal with the song? What's the other stuff?
Meter and stuff. I forgot to turn them on. Everything's in there, and then, like, all the probes and.
There's a meter and then there was,
Only basically we're good with this. That probe. Wait, so, go from there.
Was he able to get air conditioning going? So we made a change here, doesn't want to see. That's what I was at, because air was running from the stack. All right, so you can see up there, is he's, couple of changes we made in Measurequick is, one new one is you don't have to turn on your tool, you don't have to go to your toolbox anymore to turn on your tools. As soon as you turn on your Measurequick app, it'll pick up the probes and it'll just start putting the targets up. So right now, he just turned on the return air probe and he turned on the outdoor air probe on the system, okay? And if we look here in a second here, he's gonna have, he turns them on, a suction line, superheat, subcooling on there. I'm gonna deactivate the probes for a minute, just throw some demo data in for just a second here. And there's a gear up at the top here. If you tap on that gear and you scroll down, you can put in, normal operation for a system, so that's gonna throw some targets in there. Now, you'll notice that these targets, they aren't the same anymore, they're a little bit bigger. And what I did here was we took and set up that airflow, like on the suction side, we were having a lot of people, they weren't setting the airflow up for a piece of equipment. So in other words, you can do 350, you can do 400, you can do 450. Any one of those airflows is correct, it just depends on the latent sensible split that you want on the machine, right? But if you don't, so what we did is we said, okay, well, we're getting a lot of people that aren't adjusting that, so we're gonna put in the full range of airflow. So if you slow your airflow down to 350, it'll be closer to this end. If you go up here to this end, it's gonna be closer to 450. Right now, this is 379 per ton, so it's just below that. Same thing with the high side pressure. Now what happens is when you benchmark the system, I don't think, he's got pressures on. I got pressures on. I'm gonna hit benchmark. I gotta do a project here. Let me just open up a quick project. Just unlock this real quick just because I'm doing a. So when you go home here and you set the benchmark, notice those targets will tighten right up, okay? And now what it did is it took that huge target zone that we had and it narrowed it down, saying, okay, now this is the range that it should run in. So if I open that back up again, I can just hit the plus key down here and clear the benchmark, target will back up, right? So the idea here is when any suction pressure anywhere in that range is okay, but once you get it dialed in, it's gonna dial it into a more definitive target. Now, why would we want to shrink down the target zone on a machine? What's that do for us?
When you come back to it a couple of years later, you got a reference point on where
you know exactly
what's changed.
You know exactly how it's supposed to run. And what do you think it does for diagnostics, right? Because here's the question. If I told you the system had an overcharge on, or let's say an undercharged fixed orifice system. May have, right? You'd expect to see low suction pressure, high superheat, low subcooling, low head pressure, right? Undercharge of a system, classic conditions. But if you can't tell me what the pressure should be, then you just lost two of your primary drivers for that diagnostic chart, right? Most guys can't tell you what the pressure should be on the machine. They just don't know. They don't know. They can tell you if they're really high or really low, but they can't tell you if they're a little high or a little low. They can't tell you what's gonna happen if I raise the airflow or not, how it affects the suction pressure, or humidity, or anything else. The reason also that this target is offset, you notice that this one's sort of centered, this one's offset, is this is allowable also for latent capacity increase on there. And that'll actually, if you were to blow air on the probe, you'll actually see that latent zone actually increase, because it's showing you that it's allowed to go into that range. It'll be higher than normal, but when it gets back into the 70-degree range, things will be more in range. Let me see if he's got this hooked up here. So let's see here. Okay, just started up, so we'll go ahead and we'll just connect to the probes there. And we will go ahead and
So that AC normal operation in the demo data, that's just a baseline is all that is?
yeah, if you use demo data, it's just like, so you can just like show people how the app works. Or if you want to play around with it, you don't want to populate every number by hand, right? You can put that data, and then there's a reset data down here. It'll just wipe everything out, and then it'll clear all the targets that you have in there. So now he's got this machine running, right? And we can, typically we'd start here. So obviously you'll see all the targets are dynamic, so the return air temperature is dropping. So this target's, the suction pressure's going up, this target's dropping down. We'll see what the hell's going on there. That's interesting.
I think I got it in the right place.
There's no ductwork there, so.
Oh, I'm trying, so right, so yeah, that return air temperature is dropping like a rock. Let's see what that is.
Let me swap the probes around.
Yeah, 63-degree return air. Yeah, that definitely could be the problem. Right? And this is the kind of stuff that we catch all the time, people doing by mistake. This is the kind of stuff that's garbage in. All Measurequick is a calculator. That's all it is. But it's a graphing fancy type. Yes, sir.
In general, you got the two big dials on the top, the 4 on the bottom, if it's in the blue or in the red, the 4 on the bottom, is on the top, right?
Yeah, that's right. Yes, right. It's either above or below the target. So if you tap on, like if I tap on this gauge, if I tap on this target right here, it's gonna tell me, so here's a couple things we do at Measurequick that are different. So first of all, this 410A is a blended refrigerant, right? And it's not it's what is it called, azeotropic, is that right? Azeotropic. So on blends, if they have a lot of glides in them, the refrigerant will go in at like 45 degrees the evaporator, and then it'll exit at 55 degrees, right? We used to say like the last drop, it would go in cooler and come out warmer. In other words, the coil temperature will shift as it goes through the evaporator coil. So you actually have to calculate what the midpoint temperature is of the coil, so you know what the coil temperature should be. So what Measurequick does, there's a mathematical formula. It basically uses 30%. I think it's 30% of the dew point temperature plus 60 or 70% of the bubble point temperature is the formula that Emerson came up with to calculate midpoint of the glide on the evaporator, because when it goes through the evaporator, it's different than when it's in the condenser because of the flash gas, right? So it calculates the design center of the glide, and it calculates the allowable range, and then it shows you with a little arrow if it's above or below the range, and then it tells you down below what to look for. So high suction pressure is normally a singular problem. It's most commonly caused by refrigerant overcharge in combination with high subcooling and low superheat in fixed orbit systems. High suction pressure can also be the result of high load, inadequately can return, overfeeding TXV. It can also occur when would occur with a normal flooded evaporator. For adjust refrigerant charge, verify the superheat and subcooling are in range. Verify the airflow, check for matched components, including condenser, evaporator, metering device. Right, so it walks you through not only what it's supposed to be, what to look for if it's in the wrong range. Now this machine's coming down here. We got a 76-degree return air. Does return air temperature have a range?
Sure,
It should be around design of 75 and 50.
What's the, okay, if I told you the design temperature difference is 35 degrees of evaporator coil, 35 degrees. If it's 70 minus 35, what's that? 35. If it's 68 minus 35, what is it?
Too low.
The 32. What happens at 32 degrees? Water freezes on the coil.
You can see it too on here, you can see it just drops like a rock.
And what will happen if water freezes on the coil?
Airflow goes down.
Airflow, and you're gonna have other issues, right?
In less than
So
a
when you
minute.
tap on this gauge right here, it's gonna tell you the allowable range is 70 to 85. What happens above 85 degrees? We're just too far out of design for the system to work right. So there's absolutely a range for anything on this system, right? Supplier dry bulb, why is that? Are you in the supplier? Seems like it's, maybe you got the outdoor air and supply probe mixed up too.
Yeah, I could have that.
Yeah, and that's why our we're outside the range, blood pressure's outside the range, right? So it's all garbage in, it's garbage out, so flop those two down. Now notice as soon as you flip this little thing went up there and it's telling you the system's not stable right now. So if we were to tap on this,
It's going down.
yeah, it's because you just moved the probe over in the supplier. Now, so now it should start coming into range here a little bit more. Hey, look at that.
Look at that.
Right? Now, there's no duct system on this unit, so odds are it's running high airflow. Let's just go back here to the home screen for just a minute. 368 per ton, that's not really high. Might have an oversized, is that a high efficiency system?
No. This is the one that when we first ran Measurequick on it, subcooling was extremely high. Kevin and I pulled the charge out and weighed it back in, and it was virtually the same after it ran for 10 minutes.
Yeah, now this is another mistake, this is another reason we're getting some wacky readings on here.
Whoa.
What can you tell me about that liquid line temperature?
Everything's high.
Way too high.
It's on the discharge line,
Yeah.
not the liquid line. Yeah.
Wrong place.
So, okay, so I have to swap the liquid line and the suction line.
No, the suction line looks like it's on the liquid line, and the liquid line looks like it's on the discharge line.
So we take away the
certification.
You need to mark your probes, Jim. You gotta mark them.
What? It wouldn't be it wouldn't be near as entertaining, would it?
Some of us are enjoying this. The probes have cereal. Get used to which ones.
Yeah, I just know what's in my bag and I just grab them.
The way you put them in your bag, that's what
Yeah,
I
but I normally have them marked, but I have like 16 sets of probes at the office right now, and I just grab a set when I walk out the door. Oh, there we go, 57-degree suction line, that looks better. There's some subcooling,
I don't do that, but I do.
liquid lines coming down.
Liquid line's coming down.
Hey, it's looking a lot
That's on
better.
the suction line now. So,
That's what we try.
Yeah, everything's looking a lot better now.
I got two of them in my hand.
Which two?
Uh-oh, subcooling and liquid.
He's got two in his hand and one in his
So the one, if you open it up, Tom, open one of them up. So, that's the one that's discharge line. The one you have open is discharge, the other one's liquid. One you have closed is liquid.
That's what was messing with me yesterday.
Oh, yeah, oh, that's right.
What's that box cost? Oh, 600,000?
$600.
600,000. What's the extra probe? 115?
Yeah, yeah. They're really not that expensive.
Yeah.
Now when you play with one for a day, freaking awesome, man. I love those things.
Is that better?
Yeah, it's a lot better. Still runs pretty high suction line, some pretty high subflow.
So while we're waiting for
Yeah,
that to
some
stabilize,
colors
Jim,
went in the 20s when we did this originally.
Yeah. So, now, in this, train, if that's a train unit, anyways, what's the subcooling supposed to run on those roughly? 7 to 10 degrees is typical for a train on the subcooling, unless they have a subcooling circuit. Sometimes they do have a second, you can actually see it. If you trace the condenser piping out, you'll notice that it goes down, it'll usually go 2 rows go into one, and it'll come out, and it'll be like the bottom part of the coils for a subcooling circuit.
That's a micro channel.
So, by design, let's just start out with a profile here. Is that a TXV system?
It is.
All right, so it's looking for
3 tons.
For the type of compressor, right, so the first thing it's asking is a split system, yes or no, so this is actually a package system, it's got a scroll compressor, it's 3 tons of cooling, it's 410A, it's 13 to 16 SEER with a TXV, and we use the default superheat and subcooling target of 10, okay? Anybody know why we have 10 degrees, why we use 10 degrees as default subcooling for most machines? Some go a little higher, some will go up to 20 degrees of subcooling, but,
Do you recommend not changing that setting? Like,
well, if you don't know what the subcooling should be, if you had no clue, 10's a pretty safe number to use.
Yeah, it's
Right.
enough that you're all liquid, but
All right, so what happens in the liquid line between the condensing unit and then the metering device?
Might have flash gas if it's long, a lot of pressure drop.
A pressure drop, right. So there's always a pressure drop in the liquid line due to length and lift,
or,
right?
yeah, pressure increases, it's 3 stories and the condensers on.
Or you could have a pressure increase, yep, that might be where you have higher subcooling if you measured it. But most of the time, when we're looking at it, it's gonna result in a pressure drop in the liquid line. That pressure drop, the 10 degrees of subcooling allows us to have about, I wanna say it's about 18 pounds of drop in the liquid line before we'll flash to a liquid. So on a 410A system, if you're to take that down to 0 degrees of subcooling, you can actually calculate what the drop is, but that's what that's for. So we hit submit here. So now we've got a couple different things here. We're running around 12 degrees of superheat. That's perfect, right? We got a 62 degree suction line. We're running 17 degrees of subcooling, which is still showing the subcooling's high. We also got in this the liquid line temperature is cold. Why would the liquid line temperature be cold? What's happened when we start adding refrigerant, let me ask you a couple questions. TXV is running exactly 12 degrees of superheat. Is there enough refrigerant in the evaporator? It's perfect, right? TXV, it's gonna close down and says, hey buddy, I don't give a shit what you're doing on the condensing side.
Right.
I'm gonna close down, I'm gonna maintain constant superheat in the
Backing up the
evaporator.
condenser.
If you give
Right.
it 100% liquid, yes.
Yes, no, now we're stacking liquid inside the condenser.
Yep.
Right? So as we stack liquid in the condenser, we're effectively turning our condenser into a liquid line. It's no longer condensing space, it's just a giant liquid line at that point, right? And we're cooling that liquid down closer to the outdoor air temperature. So what's gonna happen is when we have high subcooling is we're gonna have also low approach temperature, because if we tap this one more time here, what's gonna happen here, this is our approach is just how close is the liquid line temperature to the outdoor air, right? So our liquid line was about 75 degrees, and our outdoor air is 75 degrees, so they're within 1 degree of each other. So a low approach is also a good indicator we have a refrigerant overcharge in the system. Yet our head pressure on the machine's just fine. Why is our head pressure fine in the machine? There's not a lot of load. There's not a lot of load. There's still enough condensing space in there, right? So you can't just look at pressures and temperatures on their own without looking at the other variables on the machine, right?
Basically a big dehumidifier back there right now. instead of-
I got a question about like using multiple probes. If you have, cause I know you can do like liquid line 2, liquid line 3.
That's for multiple stages.
Oh, okay.
So you can do up to 4 circuits at once on Measurequick. So
Okay.
if you had like a big package unit, you know, one of those train telepacks, and it had 4 compressors, you got 4 suction probes, 4 liquid probes, 4 supers, and you can switch between circuits, circuit 1, 2, 3, and 4. Then it'll also, depending on it also calculate the splits. You can have a split system. Let's say you have 4 compressors, but you have fixed airflow. So with 1 compressor on, you might get 5 degrees of split. Turn 2, you get 10 degrees. Turn 3, you get 15 degrees. 4, you get 20 degrees of split. So, and Measurequick will also recalculate what the target temperature split should be for each compressor circuit, and then with all 4 running. So,
Where do you program that in?
in your profile. So when you set up your project, let me just exit this project. Down here, there's there's 2 things here. There's multi-stage and multi-circuit. Multi-stage means it's one refrigeration circuit up to 4 stages. Usually it's only 2, but with variable refrigerant flow, we're allowing people to like capture it at 30%, 50%, 75%, whatever they want. Multi-circuit means there's more than 1 circuit of refrigeration. So when you select multi-circuit mode, you select the number of circuits, and then you could have like 2 sets of probes, and you're gonna have, then you could map them for suction pressure to liquid pressure to suction, whatever you want.
Jim, along those lines, you got a single circuit dual compressor, which one would you use?
A single circuit dual compressor, just multi-stage. Yep. So let's go back here and, we'll just start this blank again.
So wouldn't that be multi-circuit with two compressors?
No.
Multi-stage, you got one compressor, multi-speed.
Right, it's one circuit, right? So think of it as just a refrigeration circuit.
I'm sorry.
All right, so we'll go back into this. Project is just information about the project. And we'll just fix that. Oops, I can't type. Then hit continue. Job site. This is the physical building you're working in, so you would just mark the building. It's gonna pull in. Now, this is where you could actually name the site here.
This Groom Lake is what we mapped it as.
Hit done. Your address here will come in, so you do this thing. Is that, I'm sure, is there two D's in clad?
Two A's. Two A's, one D.
God, you guys don't spell that thing right for sure. All right, and then we'll flip this address is the same, so it's gonna pull up your address automatically. All right, we'll hit continue, continue. Now this one, this is important. This is where you physically mark the piece of equipment. So right now it's thinking we're in the shop, but let's imagine we're on this piece of equipment. We just drag this pin over and drop it on that condensing unit.
You wanna back up one, cause I think the address that came up with was wrong.
So we can change that. We can go into the job site, and if we gotta change the address, cause you guys are.
It's 305.
So now if you hold down your space bar on an iPhone, you can actually go across and,
What?
yep.
Yeah.
Oh.
You can get a.
My kids were.
Does that work in Samsung too?
I'm not sure, but I know on an iPhone it does, because that's what I have. All right, so this is where you mark the piece of equipment. Now this is the geolocation of that piece of equipment. This is the pin that's gonna be associated with it forever. So this is where we get our condensing unit make. And was that a YCD?
Myron, do you remember what it is?
No, I think it's a GAD.
That's right.
GAD 036 LOAB. Sounds good. And we can take a photo of that. We want to take a photo.
Whoa!
Use a photo.
Unit's dirty.
System profile, evaporator fan type. So this is where you're gonna pick your system configuration. So it's a package, PSC. It's 3 tons of cooling, 410A, 1316. You can put in the refrigerant charge if you want, put in the factory charge, and then if you have any extended performance ratings, you can put those in, but you don't have to. Installation information, location, what do they roof for the ground? In this case here, it's a ground unit. It's not zoned, so we did continue. Electrical information, condensing unit, so it's just single phase, 208, 230.
3-phase, 208, 230.
Yeah, so
With three phase.
Evaporator fan type.
Oh, 208, 230. Is it single phase or 3-phase evap? It's probably single phase.
Three.
Is it?
Gonna be 3.
No, it doesn't have to be. A lot of train stuff uses single phase motors.
On the evaporator?
On the evaporator fan, yeah.
On those little.
Yep, on the littler motors, anything under a horsepower is typically gonna be a single phase. So, and they do that on condenser fans too. When you look at a 3-phase unit, the way that you tell right away, if you open up a train unit, and it's 3-phase, and there's a capacitor in there. If there's a capacitor in there, it's single phase. Yep,
The VAP is 3, Jim.
alright. Hit continue, we'll hit continue. Filter information, so we'll tap it to set the date like we changed it today. Filter type, we'll just say it's 40% pleated. I don't know, what size filters are those? It doesn't matter, we'll just make it up here.
I think they're 16, 25.
25 by 2. And there's probably 4 filters in there, hit continue. Now we're to the measurements. Now, the only thing we gotta do now is just take electrical readings off the piece of equipment, right? And it's showing us that there's some diagnostics here, so let's go back in and just take a peek here. So it's telling us the system's operating with undetermined characteristics of liquid line temperatures below the outdoor ambient. Let's take a peek at that, see what's going on there. So we got a liquid line that's 74 degrees and our outdoor ambient 76 degrees. So it could be you're near pulling short cycling air or something around that probe, right? Because there's
We
no
got the
duct.
tap blasting right below the.
Yeah, there's no duct system on there. So that's sort of a notification and it's not stable. Let me just clear this for just a minute.
I'll move the outdoor sensor.
So the liquid line below the outdoor air, what else could cause that?
Dryer.
A dryer could definitely cause it. What else could cause it? What would be a more common cause, you think, than the
Low
dryer?
ambient conditions.
Well, ambient won't ever, it can only get down to ambient, unless it's what? We talked about this earlier, this is why you can't test the system when it's raining.
Evaporating moisture.
Evaporating moisture, so you just wash the coil, it's still wet, evaporating moisture off it, so it'll tell you if you tap on this, if you didn't know, you just tap on that button. It says on a proper operating system, the liquid line will not fall below the condenser and air temperature. Those systems flags typically caused because of wet condenser or liquid line restriction or plug dryer inside the unit,
Manty valve.
right? So verify the condenser is dry. A wet condenser will produce additional evaporative cooling on liquid. Condenser is just washed, and taking a long time to dry, use a leaf blower or shop vac to exhaust and blow the water out of the condenser. Is dry, check for liquid line restriction or plug dryer that's causing the pressure and turn temperature drop in the liquid line. If the system uses a slinger to throw water in the condenser, this is typical on like window air conditioners, things like that.
I'm gonna keep doing it.
Yeah, then you're screwed. Yep, disregard that flag, that's what it says. Right? So then suction system may have an overcharge, right? So now if I click on the minor faults here, right? So there's a couple faults there, and these are bouncing around because it's still, subcooling is too high, approach is too low, liquid line temperature is too low. It's picking up two faults that we're keying in there, the other one we might be ignoring on there, but those are the key problems with an undercharged refrigerant. All right, and we got really, really high suction pressure on this. I think we're pulling in return air that's not representative of, let's see, our outdoor air is 74, our return air is 68, so we're definitely short cycling air in there, right? And so it's seeing what it's doing is the return air it's seeing 68 degree air, but it's actually pulling in a mixed air. This is like stratified air again. Wherever we're close to, if we move the probe the other side, it'll probably go right into range. It's just seeing that cold air temperature, and that's why it's giving us an issue. Now, once we have the system the way it was, let's say that this is the way it's supposed to be. If we set a benchmark here, and it's telling us we're going to benchmark under duress, and saying, hey, you idiot, the charge is out of range, but maybe the customer won't fix it, right? So it's like, hey, I told them it's this, but I got to benchmark it so we know this is the way I left it. So I'm going to benchmark this under duress. It's going to tighten those targets up. It's going to tell you the system's benchmark, and it's going to line up the targets like that with the 20 degrees of subcooling and the problems. This is where you put in the notes that it was benchmarked under duress, you know, that there's a problem with the unit. You know what under duress means? It means you're doing something you know you shouldn't do.
Against your will?
Against your will, yeah, that's what it means. Okay, so that's why we use that particular word. The flag goes green because it's saying, hey, it's what it is. Now, can you take, Tom, can you throw just a panel on top of that condenser fan just to block off the condenser a little bit? So now it's benchmarked, and now a year later we're gonna go out, the condenser is gonna be dirty. So I want you to just watch what happens here. Let's watch our diagnostics live for just a second here, so you see how this, oops, went in the wrong thing. I'm gonna click on the flag, and I'm gonna leave that reset faults button up because I have it cleared out so the stability faults is not there. So as soon as he plugs that condenser fan up, now we're getting 4 symptoms of dirty condenser, and it could be an overcharge. Right now we know it already is overcharged, but right now it's picking up the dirty condenser. So and it's going to bounce around a little bit until it's stable. So you might get some different flags in there. Now, why is it saying the TXV bulb may be loose? Well, let's look. What happened as soon as he blocked the condenser off? Oh, superheat. Right, we forced the head pressure way up. The TXV couldn't respond fast enough, so it just jammed the liquid to the TXV and dropped the superheat in the toilet. right? So Measurequick, it really can't evaluate a system until it's stable. What it did is it shoved that, now what's the TXV doing? It's closing back down. Because it's saying, hey, I'm not gonna overflood my condenser, it's just throttling it back down. So eventually what it's gonna get is just an overcharge. So we got a high liquid line temperature. We're also gonna have a high approach temperature now. So we click on approach, or approaches to the roof. And then these are all symptoms of a dirty condenser. If we tap on the minor faults, the liquid line temperature is too high, condenser pressure is too high, compressor ratio is too high, approach is too high, right? Those are all symptoms of a dirty condenser. So go ahead and pull that back off there so we don't kill it. He really blocked it.
It's still running.
You asked them to.
Yep. All right, well, I don't wanna run you guys too much over. I know it's 7:30, we're past quitting time. But any questions I can answer before we wrap this up? So now you get an idea how to use it, benchmark it, and then, you know, we're all done. We just generate a report here, so if we were all done with the system, we just go back into our project here, we save the data. We just didn't make electrical measurements here. We'll hit share, export PDF, and generate the PDF, and then you're gonna get your report. Now, this one, I have range indicators on here, so it's showing what's too high and too low. Everything else got a check mark on it. These little symbols are showing us what tool the measurement came off of. So this came off of field piece probes, right? And then we've got, you know, all the different measurements in the report. This is more for the office than it is for the customer.
They won't understand that stuff.
No, they won't.
The office?
So sensible. This,
Don't get it.
now this system probably is running a little higher sensible efficiency just a minute ago. Let's see what it is right now, actually. So that, let me ask you guys a question here. Let's look at this just for a minute. I'm gonna keep you guys for just a second longer. All right, so here's what I want you to notice.
No, I put the panel off.
3-ton machine. Measurequick saying it's doing 2.8 tons of cooling. That's what it should be doing. We're doing 2.4. We're only doing 83% of the normalized cooling, right?
Yeah.
We're doing 98% of our sensible capacity. We're only doing 50% of our latent, right?
Yeah.
That machine's running perfect. Latent load is standby capacity. Whenever you look at latent capacity, it's there if you need it. Guess what? The humidity is pretty low in here. We don't need to remove much humidity. That capacity is going unused. That machine is fine. This is what's telling you that machine is running good. So you always want to look at your sensible capacity. It should be 95% or higher on a proper operating machine. We allow it to go down to 90% Measurequick because we've just found industry-wide, you just can't, but I always shoot for 90% right here. It's running 99.7% of a sensible capacity, which means that this sucker's running perfect, right? Even though we have an overcharge on there, it's still running, the machine's running okay. Now, this would start to drop if it was hotter out in the shop. We got up to like a 95-degree day. We don't have enough condensing space. Liquid line's gonna go up, sensible capacity's gonna drop. It's just right now it's running good because it's doesn't have a lot of load, right? But that is what tells you this, tells you the sign. Estimated airflow calculation on there's actually very accurate. We've compared this against NIST on there. There's their temperature split. Now, here's a good question for you. Target temperature split on this machine is 13.5 degrees, right? 13.5. Think about that for just a minute. Well, part of it's because we set the airflow is a little high on this. This is running 1,500 CFM airflow, which is almost 4 ton of air. Right, when I benchmark the system, so I'm saying it's more set up for almost desert climate, 450 CFM per ton or so, right? And the other thing is that if we cleared that temperature split, that benchmark out, it would probably look for a higher split. But the other thing here is, the biggest thing is just the high airflow in this. So we need to lower the airflow down to get split. But the benchmark, the reason when we benchmarked it locked that split in as being okay. Okay? So I just recalculated. Here's our filter face velocity. That needs to be below 500 feet per minute. So this got plenty of filtering in that rooftop here.
Let me ask you a question, Jim.
Yeah.
When we started, again, originally, the subcooling let us down overcharged that. So when we pulled it out and weighed it back in and came up with the same problem, is it really a problem at this point?
Subcooling?
Well, the manufacturer is telling us it's 3.3 or 3.4 pounds, whatever it is, and that's what we have in the equipment.
So, one of the reasons, if you weigh the charge back in, I'd be real curious to see what Train calls for in that unit. If that's what if you weight it in and that's what it is, that's what it is. You benchmark the system at that. You know, I mean, it's just literally as simple as going into the profile here, go into system info, and I tell it that my target subcooling is not 10, it's 20. And I hit done, and now the subcooling issue is gone, right? It's just that Measurequick is using that, but it's got a high liquid line temperature on there because it's higher than it should be. Because it's calculating what the liquid line temperature should be based on the outdoor air conditions, but who knows, we got a little bit of an issue with the short circulation of the air and stuff. It's could be garbage in, garbage out on that machine. Now, I don't have this on a benchmark anymore either. I cleared the benchmark out, and it's telling us, hey, it's in the range. Now, I know the suction pressure is high here, right? But that's not really an issue. It's just high suction pressure, right? It's got normal head pressure. Its head pressure is not low. It's not a compressor valve problem. It's because the airflow is that high, right?
Well, with no ductwork on it.
And
just,
no ductwork. Yeah.
You know,
You're gonna have more.
Yeah. So it's telling you,
What's
if
the
you went
indicator?
into the minor faults, what this is telling you, if you go and hit this flag here, and we look at the minor faults, there still are minor faults, okay? Because the outdoor air temperature, it's picking up some things. Again, this is picking up discharge air from somewhere. Evaporator pressure is too high. Total capacity, approach is too high. There's some things here that are screwed up on this, but there's nothing in the minor faults aggregating to a major fault, right? It's just telling you these readings are a little weird on there, and it may be the best you're gonna get it. All right, well,
as it sits.
How will you measure face velocity with a temperature probe?
it's magic.
Yeah.
No, it's okay.
Formula, right?
No, it's you take square inches of filter, divided by 144, that gets you square feet, right?
Yeah.
Then I calculate airflow Measurequick. I know my CFM, divide my CFM by my feet of filter space, and I get feet per minute. So, because cubic feet divided by feet, and I get feet squared.
Well, that's tricky.
It is, it's magic.
What's the airflow side look like? Because they have the static probes in there too.
Airflow, it's running half an inch of static, and it's running high airflow. So target, if it's 3 tons, 1,200, and we're running about now. Here's a question for you. ACFM versus SCFM. Anybody know the difference?
Actual one standard.
Actual, what is a standard CFM?
68 degrees,
X number of
50%.
percentage humidity.
A standard CFM has a mass of 0.075 pounds per cubic foot.
no,
We're not cooling CFM of air, we're cooling pounds of air. 0.075 times 400 is 30 pounds per minute per ton. So you're actually cooling 30 pounds of air per minute going across the coil, or if it's a 5-ton system, 150 pounds of air per minute going across the coil.
That's where the location, altitude data and all that.
That's mass flow, right? So if you took 0.075 times 2,000, it's 150 pounds of air. Measurequick is actually calculating down here so the return air density is not 0.075, it's 0.072. Right, so I took 0.072 actual CFM. What it means is we're moving 1,560 actual CFM to get an equivalent of 1,400 standard CFM of air. So when you're setting up equipment and it's really hot and humid, you got to make sure you have enough standard CFM. The actual CFM, because a ESC fan, will move is a constant volume machine with a variable mass flow. So in other words, if it's moving 2,000 CFM air, it's got 2,000 boxes of air, it's just throwing 1 cubic foot box of air down the ductwork. Doesn't give a crap what's in the box. The box, it gets heavier, it's gonna move more mass. The lighter, it's gonna move less mass, but it's gonna move 2,000 boxes of air down the duct a minute. Doesn't care, right? ECM works off RPM and torque. ECM goes, ooh, these boxes are a little light. I'm gonna throw more of them. So an ECM will move a constant mass flow. A PSC will move it's a variable mass flow device, right? So two different motors. So a lot of times what you'll see is your ECM, when it's hot and humid, if it's set for 1200 CFM, it might be moving 1400 CFM of actual air to get the correct standard air. And your PSC motor will be moving 1400 actual CFM. And you can leave it there because you know once it cools, the air cools that back down, it's going to be right in the right range, right? So you need to just watch standard and actual CFM when you're doing the air balancing on there. All right.
So ECM moves standard CFM?
ECM is a variable volume flow
Yeah.
with a constant mass. So it moves the same pounds of air all the time.
Okay, constant.
So as the boxes get lighter, it throws more. As the boxes get heavier, it throws less, but it's always going to throw, at 400 CFM, it's going to throw 30 pounds per minute per ton. A PSC motor is going to throw 400 boxes. So it's going to have a constant volume with a variable mass flow. All right. So again, if you ever think you have a bad day with Measurequick, just remember somebody's got to program this shit. And it's much harder to figure out. Believe me, when you look at systems all day like I do, sometimes your head wants to explode because you're looking at so many variables trying to figure out if everything's doing what it's supposed to do right. But it's gratifying. I like doing it, so it's a lot of fun. But it's sort of a sickness at the same time. So
It's an addictive sickness.
yeah. And once you have the data, like Terry said, you can't live without it. Once you start watching the stuff, you see it all happen in real time, and you see things like the trending. You know, so working at our total capacity trends, we can look at let's see what our subcooling's doing here real quick. So here's our superheat and our subcooling, right? That's the valve modulating. So, you know, your subcooling actually is changing. Anybody know why this is changing a little bit? What happens every time the valve opens or closes? What happens to the head pressure?
Haunting.
The head pressure drops, the valve opens, the head pressure drops, the valve closes, the head pressure goes up. You're actually seeing the impact of the valve modulating on the high side.
Yeah.
So.
Have you seen high subcooling as more common since the microchannel coils came about?
Well, is this microchannel out here?
Yes.
And this is why you're seeing it. So normally you would never see this on a PSC,
Yeah.
or I mean a regular copper coil, because it just microchannel's so goofy.
Because
Now
so
the other
quick
thing
and
is,
sharp.
I didn't realize it was microchannel.
Yeah.
Because when you say you pulled the charge out and weighed it in,
Yep.
microchannel condensers have a different superheat or subcooling targets depending on the temperature.
Okay.
So you could very well, because the coil is highly efficient on a mild load, have very high subcooling like this, because it's getting it closer to the ambient temperature. So you'd have lower approach, you'd have higher subcooling. Where on a hotter day, it's going to be just the opposite. The subcooling will start to drop down.
Is there a variable that you can tag?
What's that?
Is there a variable in your settings that you can say, hey, this is a microchannel?
No, I haven't had any microchannel. The only thing I don't have in my office is a microchannel, so I might have to come down here and play this a little bit,
Sure.
see if we can make something on it. So, if I had a switch, it would just tell you to buy a regular condenser.
Because you can fix those.
Yeah,
Really? You would rather have a regular condenser?
I can't stand microchannel.
I can't stand friggin' split coils. I think they're the stupidest things ever.
Yeah.
Well, you can have a regular coil without it being.
Yeah, but why did they make them split? That's all I wanna know. Is there no such thing as cottonwood anywhere but Cleveland, Ohio?
Hey, it stays clean on both sides.
Yes, the middle.
It does
It's
that,
the middle of
that's
the
for
t-shirt.
sure.
Yeah. All right, well, hey, thanks for giving me a few minutes tonight.
Thanks.
Oh, here, I can probably squeeze something in on the combustion side.
So where are you working tomorrow?
You go to
Where are we now? Pen and tape on.